Hello and welcome to the third lecture in part 3 of the course New Technologies for New Physics offered by Nussmeisis. This lecture is dedicated to tracking detectors, which have followed me almost all my life as a particle physicist. To remind you, my name is Olaf Steinkamp and I'm a senior scientist at the University of Zurich in Switzerland. Tracking detectors are a very important ingredient of almost all particle physics experiments, and we use them to measure the trajectories of long-lived charged particles. We want to do this first of all in order to determine the origin of the particle, to see whether it was produced in the so-called primary vertex of the event, the point in which the beam particles collided and interacted with each other, or in a displaced secondary vertex from the decay of a short-lived particle. Combining information from several trajectories of long-lived particles, we can reconstruct the positions of these secondary vertices as well as that of the primary vertex, and reconstruct the flight direction and the decay length of the short-lived particle. For the kinematic reconstruction of the event, we have to measure the momenta of the long-lived particles, which means that we have to measure the direction of flight and the magnitude of the momentum, which we can get from the bending of their trajectory in a magnetic field. Tracking detectors also play an important role in linking together the information from the different parts of the experiment. For example, linking to the particle showers reconstructed in calorimeters or the photons measured in Cherenkov detectors. But I want to focus now on the measurement of the magnitude of the momentum in a magnetic field. If we have a charged particle moving in a magnetic field, we get a Lorentz force, which is always perpendicular to the direction of motion and therefore forces the particle onto a bent trajectory. If we know the strength of the magnetic field, we can calculate the momentum of the particle easily from the bending radius of its curvature in the magnetic field. If we express the charge of the particle in units of the elementary charge, measure the momentum in GeV over c, the magnetic field in Tesla, and the bending radius in meters, we get this very easy to remember relation P equals 0.3 times B times R. Now the picture shown here on the right depicts the situation in a typical colliding beam experiment. I'll come back to this in a minute, but I want to first discuss briefly the setup of a fixed target experiment. Now you may remember in a fixed target experiment we have a beam of high momentum particles which we shoot into a target at rest. The center of mass system of the collision is forward boosted in the laboratory system, which means that all the particles are produced in a forward direction. And the typical setup of the tracking system then looks like depicted here. We have a dipole magnet with field lines orthogonal to the beam direction, and we have a set of planar tracking chambers, tracking detectors in front of this dipole magnet in order to measure the origin of the particles as well as the direction of flight in front of the magnetic field. And then we have a second set of planar tracking detectors after the magnet in order to measure their direction of flight after the magnet. And from the bending angle between the flight direction before and after the magnet, we can reconstruct the momentum of the particle. In a typical colliding beam experiment, the center of mass system of the collision is at rest in the laboratory system, so the particles are produced in all directions. And the typical setup of the tracking system then is as depicted here. We have concentric cylindrical tracking layers surrounding the interaction point here and immersed completely inside the magnetic field. And we measure the bending of the trajectories of the particles in the plane orthogonal to the beam axis. Now I want to briefly derive how well we can reconstruct the momentum. What factors determine the momentum resolution, the precision with which we can measure the momenta. And I want to derive this from this very simple example shown here on the right, where we have 3 measurement points along the trajectory of the particle, all 3 measurement points inside the magnetic field. The distance between the first and the third measurement is given by this length L here, and the bending radius of the trajectory is given by R. Now we can calculate the sagitta of the trajectory here by the difference between the bending radius R and the length of this side here of the triangle, which is thus given by R times cosine phi half. Now if we assume that phi half is not too long, we can make this approximation here for the cosine, and we get that the sagitta is just given by R times phi squared divided by 8. Another relation we can derive from these triangles is that L half the distance between the first and the last measurement here, that is this side here of this triangle, is just given by the bending radius times sine of phi half here. Again, making the approximation that phi half is not large, we just can calculate phi then as L divided by R. And the third equation we get from the Lorentz force, that R is given by P divided 0.3 times B. Now, putting these three results together, we get that the sagitta can be expressed as 0.3 divided by 8 times L squared times B divided by P, the momentum of the particle. Now assume that we measure each of these three positions here with a resolution sigma x. Then we can do simple error propagation from x, sigma x, to the precision on the sagitta measurement, and from there, using this equation here, to the relative momentum resolution sigma p over p. And we find that the relative momentum resolution is given by square root of 3/2 times sigma x, the measurement resolution of our tracking detector, times 8 times p, the momentum of the particle, divided by 0.3 times b, strength of the magnetic field, times L squared, the distance between the first and the third measurement. Now this is a very simple derivation, but if you do this for n measurements in a homogeneous field, which has been done by Mr. Gluckstern back in 1963, he found that this equation essentially still holds true. Only this factor in front of the terms here changes, of course, with the number of measurements you have. Now looking at this equation, we can see that the relative momentum resolution deteriorates linearly with the momentum of the particle. This makes sense. The higher the momentum of the particle, the smaller its bending in the magnetic field, the more difficult it is to measure the curvature of the trajectory, and therefore the worse our momentum resolution becomes. It improves linearly with the detector resolution. That also makes sense. If you can measure the positions along the trajectory more precisely, you can measure the bending radius more precisely and therefore get a better momentum resolution. It also improves linearly with the magnetic field. Again, stronger magnetic field means stronger bending of the curvature, easier to measure, better momentum resolution. But the main point here is this L squared. So the relative momentum resolution improves quadratically with the length over which we can measure the trajectory. So the distance between the first and the last measurement. And that is one of the main reasons why experiments at the LHC are so huge, because we want to measure the trajectory of the charged particles over the longest possible distance in order to get the best possible momentum resolution. And you see here the experiment. This is from the Atlas experiment. The coils of the magnet, the tracking system would be inside this, and you see by comparison, a person, just to give a sense of the scale here. So this is the contribution to the momentum resolution from the measurement of the trajectory. But there is another contribution which is very important, which is due to the interaction of the particle in the detector material. Whenever we have multiple scattering of the particle inside the material of the detector, its trajectory is disturbed and we deteriorate our momentum resolution. And the same is of course true for any energy loss that the particle suffers in the material of the detector. If it loses energy, its momentum changes, and therefore also our momentum resolution changes. Now, just looking at the multiple scattering term here, The mean scattering angle in a plane is given by this complicated looking equation here, where we have here 1 over beta, 1 over the momentum of the particle. Here, crucially, the amount of material expressed in radiation length. Now we can do again error propagation, and what we find is that the effect of the relative momentum resolution from multiple scattering is given by this expression here, where we have the amount of material of the detector up here, beta, we divide by beta, and we divide here by the magnetic field. So at the LHC, where we have high momentum particles and all particles essentially have beta almost to 1, this gives a constant term as a function of the momentum, but we see that the amount of material of the detector is very important here. This is even more important, by the way, at low momenta. If beta becomes smaller than 1, this term really explodes at small beta. So if we have experiments that measure at low momentum particles, this term from multiple scattering becomes extremely important. But we see the effect of this even at the LHC. I show here 2 sketches of the layouts of the tracking systems of the Atlas tracking system here on the left compared to the LHCb tracking system here on the right. You remember the LHCb detector looks more or less like a fixed target experiment, although it is actually a colliding beam experiment. Now in Atlas, a lot of effort was put into providing as many measurements along the trajectory of the particle as possible, because in Atlas they look at very high momentum particles and they need a lot of measurements in order to measure the momentum of the particles reliably. And you see over a distance here from r equals 0, this is the beam axis, out to 1000 millimeters out here, we have constantly tracking detectors, and the biggest gap that we have in between any 2 tracking detectors is less than 18 centimeters here. In LHCb, by contrast, lot of effort was put into having as little material as possible in the tracking system. This results in this very sparse layout here, where we have a vertex detector here surrounding the interaction point, 2 layers of tracking detectors in front of the magnet, 3 layers of tracking detectors behind the magnet, and here over a distance of 5.5 meters we have no detector at all, only air in between here and here. Now this makes track reconstruction, of course, a lot more difficult, but it also has the effect that we've seen already in an earlier lecture of giving this excellent momentum resolution that we see in LHCb. This was illustrated here by these 3 Y resonances, where you have here the Y1s, 2s, and 3s states, and we saw in LHCb we can very cleanly separate between the 2s and the 3s state here, because the momentum resolution is so good, and therefore also the invariant mass resolution on these resonances is extremely good. In Atlas, because we have more material in the detector, the momentum resolution is less good, and you see that the 2s and 3s states here cannot be separated cleanly from each other. Now there's another effect of material on the tracks, and that is due to hadronic interactions, and this I want to illustrate with this example from the CMS experiment. You see here on the left the track reconstruction efficiency for muons as a function of the so-called pseudo-rapidity eta. Pseudo-rapidity essentially is a measure of the polar angle of the particle with respect to the beam axis. And we see for muons we have here excellent reconstruction efficiency of close to 100% over a whole wide range here of angles, and it drops only here at the very edge here, where we essentially are at the edge of the detector. The picture looks different for pions. For pions we never reach 100% efficiency here. It always hovers around 80 and 90% here, and we see there is a minimum in the efficiency here at around an eta of 1.5. Now this eta of 1.5, as I said, eta corresponds essentially to the polar angle of the particle, and this eta of 1.5 corresponds just to the angle where we have the transition region between the barrel part of the detector here and this end cap part of the detector here. So why is the reconstruction efficiency for pions lower in this part of the why is it lower overall, and why is it particularly low in this part of the detector? Now this is because pions, in contrast to muons, also do hadronic interactions in the detector material, and if they undergo a hadronic interaction, the trajectory can get a large kink, or we even get a shower of secondary particles, and we essentially lose the pion completely. And if this happens before the pion has left enough hits in our tracking detector for us to be able to reconstruct the trajectory, we lose efficiency. Now, the fact that the efficiency is particularly bad in this region here, in this overlap region between the barrel and the end cap detectors, is due to the fact that in this region we have a particularly large amount of material in the detector. And this plot here on the right shows, again as a function of eta, of this pseudo-rapidity, the amount of material in the detector. And you see that you have a clear peak here around this 1.5, where we had this drop in efficiency. There's also a breakdown of the different contributions to the amount of material. And what you see is that the sensitive detector, so the material of the actual detector itself, where we detect the particle, is given by this brownish part here. This is this small contribution down here. Most of the detector material that the particle has to traverse is actually due to so-called dead material. These are support structures, cooling, cables, electronics, and other stuff. So this is extremely important for a successful experiment, to have as little material as possible, and in particular to remove or to minimize this amount of dead material in the way of the detector. And that this is not always easy. You see here from this photograph of the tracking, the silicon tracking detector, the barrel part of this in the CMS experiment, you see this enormous amount of cables that we need, or that they need, in order to read out the detectors, to supply operating voltage, high voltage, all these signals that the detector needs. And all these cables have to go, now let me try to go back, sorry, have to go through this gap here between the barrel and the end cap detectors, and that's why you have this huge amount of material here in this region and this drop in reconstruction efficiency. Okay, with this I'm at the end of the first part of this lecture. I have a little quiz for you, which should be totally trivial for you to answer, and we'll of course give the solutions when we meet next week.